Definitely. And why does it disappear as soon as you turn off the server? Right. So it's at the mercy of the server process. Okay, that means basically that it's being stored in RAM, right, which is ephemeral memory. So you guys learned a little bit about this with Gabe during the first lecture on data structures. But there are many kinds of memory, and the most ephemeral of them is called RAM. And as soon as you boot your computer, a number of documents are loaded into RAM. Like anything that you keep on your desktop, in your desktop folder is loaded into RAM initially, which is why if you like ever have like a slow computer and you take it to the Apple store and they look on your computer and they see a number of things in your desktop, that's the first thing that they do. They just remove all that stuff from your desktop into your home folder, because a number of things are being loaded into RAM that don't necessarily need to be loaded into RAM. Okay, and that of course the fewer things that are having to be kept in RAM memory, the faster your computer will be. Great. So basically, because it's ephemeral, right? It's not persistent, and we consider true persistence that which is loaded into disk. Okay, because if it hits disk, that means that we can retrieve it via memory APIs. Okay, and that sounds a little confusing, but that means that basically it's not being created when the server boots and then destroyed when it ends. It persists beyond the life and death cycle of your server. Okay, because it's going to be stored on the hardware of your computer. Does that make sense? Cool. So that's important. So right. So when we create just like a vanilla JavaScript array and we throw objects into there, that's just being stored in memory. It's not hitting disk, right? And so I would say that that is the biggest limitation of your Twitter apps right now. It's that it isn't benefiting from true persistence. And in some ways, I would say that's like the only thing keeping it from being a real app at this point. Because you guys have your views and they're kind of ungainly. They're like Swig HTML templates, really unpopular these days. No one's really using that anymore. And then you have your server process. You have Express. So you have request and response. We have client side. We have our server. But we don't have yet this third component that is critical to all web apps, and that's the database. And so that's what we're going to learn about today. We're going to learn about relational database management systems, okay, otherwise known as like SQL databases. Cool. And then we're going to learn the SQL syntax. We're going to play around with querying so that starting with the next workshop after SQL, which is what we get to tomorrow, the following day, we're going to refactor our Twitter app so that they use a real SQL database, SQLite. And that's when I would say you guys have built your first app in our curriculum. It's when it's using a SQL database. So that's cool. So that's a roadmap. So first, let's like get into databases. So setting aside the fact that every major web app uses a database, thinking of the tools that you now have at your disposals, how could you folks achieve persistence without using a database? Yes. Absolutely. That is exactly what I was looking for. You could read and write to a file using your file system module that you guys know is built into Node. So with each tweet that you post to the back end, you could have an express route that received that request and then said fs write file and sent that tweet into a file somewhere in your file system. And then when I queried for that tweet, you could use fs read file to read that file back in and then send it to the front end. Make sense? Cool. And in fact, this is what people were doing before Oracle came along and like fixed everything. Basically, like reading and writing files. That's a little bit of a simplification, but not too much of one. It's pretty rudimentary. So cool. So let's get into this first slide, which please click. Okay, great. Appreciating databases. Databases are central. They're everywhere, and every application needs one. That's why it's very important to learn about them. Databases, especially SQL databases, are just, yes, a standard. NoSQL databases are certainly rising in popularity, but they still don't quite rival SQL databases. It's because SQL databases came out obviously decades before, and they just solved many of the major problems. And actually, the Oracle team, and I'm saying Oracle because they, it's that team that created the first SQL database. They produced something that is really quite rare in the realm of technology, which is an implementation of a theoretical model that has persisted for decades. Okay, so the first SQL database came out in 1980, and we're still using them. And really think about everything else you're going to learn with us. You're going to learn about Express, you're going to learn about Node, which you already have a little bit. You're going to learn about Angular, even JavaScript. These are all things that came out in like the last 15 years. I mean, these are all very recent technologies, and who knows when we'll be using any of those things in a decade or two. I'd say it's highly unlikely we're going to be using Angular in 15 years. Just think it's true. Frameworks come and go. There have been a number of major frameworks. 5 years ago, you probably would have been learning Backbone, maybe Ember. Okay, Node, who knows if we'll be using that in 10 years. Probably another better server side implementation of JavaScript will come out in the next decade. But SQL databases, you'll definitely be using in 10 years. You'll be using them in 20 years. So in some ways, it's like one of the most important things you're going to learn here. Okay, because these skills will definitely stay with you because you'll be using them over and over and over again. Hard to say that about anything else you learn. Right, because that's the nature of technology. You'll just be learning new technologies arise, which is why here we like to focus on equipping you with the problem-solving skills so that you can learn new technologies as they come out. Right? It's far more important that you learn how to learn and not that you learn the particular things that we're teaching. Except for this guy. This guy is like something you just like bank and just like count on. So great. They're challenging. You guys have probably heard things like scalability is like the biggest problem in web app development, or like scaling so difficult, things like this that people just like say, they don't really explain. And maybe at this point you're wondering like, why is scaling so difficult? I don't know, I've learned about Express, I've learned about Node. Theoretically, you probably know that you can spin off another instance of your application without too much trouble. Maybe you've heard about Heroku, which makes scaling like pretty simple with regards to just like the number of lines you have in your app. When people are talking about scalability, they're really just talking about database issues. That's the only reason why it's hard to scale to serve like 5 million people or 20 million people, even 100 million people. It's very simple to create an app and then spin off another instance of it and have some users use that instance of your app and other users use instance A of your app. It's far more difficult to figure out how to share data across those instances. How do you scale a database so that it encompasses the user documents of your 100 million users? And if I have 100 million user documents in my user table, how do I make it so that it doesn't take forever when I want to retrieve one document? Because you think if your server process has to scan 100 million documents to find just one, it could be insanely slow, okay? So the more data that we accumulate, just like think of an array, the more data you put in an array, the longer it is, the longer it could take to get to the last element in that array and retrieve it. Same thing with databases. The more data you have, the longer it takes to traverse that data and retrieve the document that you're actually looking for, right? So that's just to say that it's really the skills that a database admin has at his or her disposal with regards to just like using SQL are pretty critical. Not simply because SQL is like in and of itself can be challenging to master, but also because they have to consider very important design questions with regards to how to accommodate the expansion of an enterprise and of data, really, right? Cool. Databases are critical. When they're designed well, we can retrieve data very quickly. And not only can we retrieve it, but we can arrange it in a way that makes a lot of sense, that means something. So we can read that data, organize it, discern patterns, and then say major things like 90% of the world's data has been created in just the last 2 years. That's like probably true. I mean, no, it's like definitely true. You think about it, right? We're creating more and more data with our online profile, social media. We're able to track human emotions in ways we've never been able to do that before because people are constantly reporting about themselves online and publishing their thoughts and emotions, right? So like psychologists are salivating over these things. It's too bad that, or rather, too bad that there aren't like data centers as powerful and comprehensive as Google's at like every university, right? Because then you have a lot of academics who have at their disposal these powerful tools to read and make sense of data. This is why Google and Facebook are producing now like pretty interesting psychological research, right? Because they're able to learn so much about us through our profiles, and also because they have the best database admins on the planet. Cool. So that's just really just trying to hammer home how important databases are, and also how important SQL is. Cool. So some history. Anyone know who these people are? Any clues? Any guesses? What's that? Basically, yeah, I mean, great. Good reading of context clues. Probably has something to do with SQL and databases. So, all right, Ed Oates, Bruce Scott, Bob Meyer, Larry Ellison. Most of you guys have probably heard about Larry Ellison, right? He's like, he doesn't look this dorky now. He's got like this goatee and this sort of like guru thing going on. He's like one of the richest men in the world because he was the head of the founders of Oracle, which produced the first SQL database. And those founders were Ed Oates, Bob Meyer, Larry Ellison. Bruce Scott is technically their first hire, which is why he looks so happy. Story goes that he like heard about what they were doing, and he's a very smart guy, so he just instantly calculated the amount of wealth he would accrue just by signing on to this team and just getting a little bit of equity. And yeah, this guy is like set for life, so that's why he's like cheating so hard right there, because he's just like, yeah, money. Just like got the best gig ever. Right, so these folks, basically what they did is they took this paper that was written in 1970 by this guy, Edward Codd. He wrote this paper entitled A Relational Model of Data for Large Shared Data Banks, which is basically just a proposal for how one might structure data in a way that was general enough to accommodate the needs of every enterprise. American enterprise, insofar as he could ascertain those needs. So basically he said, okay, I'm looking at company A and I'm looking at company B, company C. At this point, pre-1970, each company is basically responsible for coming up with its own database, okay? And so they're storing, company A has a particular kind of data it needs to store. And so it's coming up with a way to store it and with its own querying language for retrieving and inserting that data. Company B is doing the same thing, which is why pre-1970 mergers were not insignificant. They're still not insignificant, but like back then, much bigger deal, because you had company A's data being stored in a very particular way and being queried in a very particular way, and company B's data being stored in a very particular way and queried in a particular way, and trying to marry those two and throw them into like a shared data bank was really difficult. And I believe Edward Codd was like one of the guys who would be like called up to assist this process as like a consultant. So like, how do we merge these two data banks and merge our querying languages in a way that saves time and money? So then he came up with this paper that was like, what if we all conform to these specifications? What if we all store data in this way and queried it in this way? And he's just throwing out ideas. But this paper was a huge deal because I believe Larry Ellison stumbled upon it and was like, this is the way. Like, this dude knows what he's talking about. I'm going to figure out a way to actually make it a reality. And that's basically what Oracle did. This is them in 1978, but the first database, SQL database, didn't come out until 1980, technically. And this paper was written in 1970, June of. So it took a number of years. Not insignificant task. Right, so they developed SQL. That's what Oracle did. And let me skip to this next one. Oh, I'm ahead of myself. This is the slide that describes everything we just talked about, how data was stored in custom data files, came up with their own querying languages, right? The disadvantages are hard to change the system, knowledge wasn't compounding. You can imagine the people who were tasked with managing company A's data and managing the querying language were incredibly valuable people to that company, right? You had like the bus problem. Like, what happens if that dude is hit by a bus? Like, we have a serious situation because he wrote that language and he came up with a model. And it's very hard to transfer this information to the next because it's not conforming to basic patterns, right? And I'm gonna sort of skip to another slide, which I think makes this like pretty clear. So SQL basically made querying languages, Oracle basically made SQL, which is a very declarative querying language. Okay. Whereas before, each database admin was more or less implementing a very imperative approach to storing data. Because again, when you're not thinking about how your system has to accommodate all kinds of data, you're more inclined to think about how your system has to accommodate the very specific data that your company has. And if that's true, then you're more likely to come up with a way of storing data and a way of querying data that is too highly customized to the particular data that you're storing for it to accommodate another kind of data, right? This is my slide explaining declarative versus imperative. So does anyone want to point out which one of these they think is declarative and which one imperative? What's that?
The bottom is declarative.
Why?
It's like easier to read for someone who doesn't have a background in JavaScript.
Yes, absolutely. Yeah, that's certainly part of it. Declarative code is like more highly legible code. It's expressive. That is certainly a facet of it. I like to think of it as, and of course these terms are relative, right? So I could show you another example that's more declarative than this one, right? We could say that this is like midway on the spectrum of declarative to imperative. But in general, one question to ask is the code going step by step through the process, or is it just explaining, declaring what it wants to have happen, right? So how nuts and bolts is the code? And so if you look at this first one, we see we have this initial array, and then we have to instantiate a second array. We implement this for loop, very rudimentary, and then we have to go about multiplying each element in this array by 2, capturing that number, and then adding that number to the array. So it's step by step by step an instruction on how to get from one array of elements to another array of elements that contains the 2 times of that element in the first array, right? Whereas this is like pretty simple and expressive and decorative insofar as I just use map, an abstraction layer, over the for loop and say, all I want is n times 2. That is what I'm telling you what I want, n times 2, and then I receive it. Map returns a second array, so I have to instantiate it myself, define it, and I don't have to add the n times 2 into the array. I just get a new array because that's how map works, right? Does that make sense? So another way to think of it is, at what layer of abstraction does the code lie? This is obviously sitting at a higher level of abstraction, which really I think is another way of thinking about declarative code. How abstract is it? This is not abstract really at all, right? I'm spelling out each step. Cool. So we can say like this is more of what companies were doing pre-Oracle, and this is what Oracle allowed them to do. Great. So SQL is sitting at a higher level of abstraction than the very highly customized types of languages that were coming up before. Okay. So knowing that, yeah, this slide. Well, I'm just ahead of myself. Great. Okay. So let's skip to this one. Yes. So what does this look like? What do SQL databases look like, and what is SQL exactly? So I like to think of like Excel spreadsheets when thinking about relational databases. You have where each sheet is like a new table, and columns would be the equivalent of keys in an object. Okay. So you might have a user spreadsheet, and in that column you might have first name. And in that sheet you might have a column first name, and another column last name, a column age, and where of course the data that sits under those columns is the actual specifications of that data. Ayana Wilson, you know, age. Duplicate rows are not allowed. That's just a point about validation, but I don't think we need to know that at this time. Again, ahead of myself. Okay, so imagine Excel spreadsheets. And what SQL allows us to do is interface with these Excel spreadsheet-like tables in the same ways that we interface with our Express apps. Basic CRUD. We create, we read, we update, delete, insert, create. Same thing. We're inserting a new row into the table. That row might contain your user information if it's a user table. Select. That's our querying. So that's like a GET request. We're selecting, we are querying our database for information. Update, same as update. Delete, delete. Great. So let's, you know, we can go on and on about this, but I think it's best to just like skip to an example that really makes it plain. So that's what I will do at this time. Okay, let's see. Speak that. Great. SQL and SQL join. So this is what we can imagine a table like this. We have a user table and we have a course table. And in this workshop, we're actually going to be focusing mostly on a subset of the IMDb database. And you will be charged with constructing queries that fulfill certain specifications in the workshop. Okay, but that database has a number of tables, a movies table, a director's table, an actor's table, and we'll ask you to do things like come up with the 10 most popular names or / like common names in the actor's table. Okay, so we'll be working with queries, constructing queries to retrieve the data that we want, that is meaningful to us. And I think it would be helpful if you imagine the data as living like this, because a lot of you have are very familiar with Excel spreadsheets, and that's just basically how it works. So in this example, we have a user table, we have a course table. We have an ID, we have a name, and we have a course. The ID field right here defines the primary key of each of the objects. Anyone have an idea about like what a primary key is and why it matters? Yes, Preeti.
The primary key is automatically assigned to every single row that you're going to add to that table. So it's like you can't have like two different keys that are both high, so you know that every row is unique based on their ID.
Absolutely. It's a universally unique identifier. It's how we can uniquely identify each object and retrieve and say something like user table, find by ID this ID, the object that has this ID. Okay? So each object in each table has a primary key, the thing that uniquely identifies it. Right? I could have, this row could also have Alice. And it could have, you know, course 2. Okay? But because it's number 2, I can distinguish this document from that document. That's just a hammer on the point. So these are primary keys. Obviously a string. Our data, with our databases, we store data of the same types that we deal with in JavaScript: strings, numbers, booleans, objects, arrays, what have you. So just imagine these as strings. And these are also primary keys, okay? But they are the primary keys of objects that live in this course table. So this is where we get to like the relational part of relational database management systems. Because here I have a column that is storing information about objects that live in another table. I'm establishing a relationship between my users and my courses, okay? So Alice is in course 1. I can look down here and see that course 1 is HTML5. Okay, make sense? Great. So why does that matter? Cool. So what if I want to find all the users who are enrolled in a course? Well, I can start by defining the column names that matter to me. Okay. So I can say I want my result set, and that this is the result set is what we call a table that's the result of a query. I want my result set to have two columns: the name of the users, the name of the courses. And that means that I have to match the information that's in the course table with the user table. And so this is particular to SQL. This is not, this syntax right here is not necessary. This is how they chose to define it. But with an inner join, I say something like from this primary table, the user table, inner join the course table. That's basically saying like fold the course table into the user table. And do that along this bridge. And this is the key part. This is like the central pattern of SQL statements, where you have table A dot foreign key equals table B dot primary key. Okay? Table A dot foreign key equals table B dot primary key. Because it's along these keys that we walk to find the overlap. So if we go back here, again, this is what I'm saying. Provide to me a result set that displays, if I take Alice, the foreign key of Alice that is the same, that identifies uniquely the document in the course table. So it's like smushed along this route. This is the foreign key right here. This is the primary key right here. Smush these together. And this is the bridge. Without this, we wouldn't be able to do this. Because we have to take the information in one table that overlaps with the information in another table to create the bridge so that we can form that relation and leverage that relation. Yes?
So in the first table, this third column course is in fact the column course ID.
Right. This column contains the primary keys of the documents in this table. This is the relation part right here. And that's the only way we can have relations, is if some tables are just pointing to information contained in other tables. And that information is always a primary key, because that's the only way we can uniquely identify the information that it lives in other tables. Okay? So it is integral to how SQL databases work that some tables store the primary keys of other tables. Yes?
And does it point or does it copy?
Great question. It points. These are objects. These are what we call object IDs. They're direct references to the information in other tables. It's weird because when you read this information, it will look like strings. It'll be like a long, especially when you get into NoSQL databases like Mongo, it'll look like a long string number, a number of like 16 bits or what have you. But it's actually technically an object ID. When it lives in the database, it exists as a reference, right? Something that can be pointed to, not copied. You guys with me? This will make more sense when we come to the Venn diagrams. I have Venn diagrams. But, okay, but this is also, the point of this is also to show you the inner join, okay? So this bit right here, select column names, the names of the columns in these two tables, this statement here, and this right here, the bridge, are common across all kinds of SQL syntax. This bit about from user inner join course is very particular to inner join. Okay, but there are two main statements that we need to acquaint ourselves with. That is the inner join and the where statement. Anything you can do with one, you can do with the other. It's just slightly different syntax. So let's look at what this query would look like if we wrote it with a where clause.
So inner join course is the column name of the user table, right?
Oh, no, not quite, sorry. Course is the course table. So this is where I say, I want my result set to contain these columns. So this is the user.name, and this is the course.name. The name column from the course table, the name column from the user table. From table name, this is a table. Inner join this table that contains this information. So these two are tables, these are column names from those tables, and this is our bridge. This is where we say the user table contains a course column that contains primary keys from the course table. In the course table, those primary keys are stored under the ID column. Primary keys, the ID column. In the user table, these same primary keys are stored in the course column. That's why we have user.course, this column, equals course.id, this column. Okay, yes?
I have two questions. So, what does it return? The next slide?
Yes.
Does it return an object or an array of things that return those next to us?
It returns a table called this whole table. And this is what we call a result set. It's the table that is a result of that particular query.
And next question, sorry if we can go back. Can we put multiple courses, like Alice, course 1, 5, 6, whatever?
Yes. It is absolutely possible to store data in that way. I don't want you to worry about that too much just now. Working through the workshop, we'll introduce that concept to you, and then we'll discuss more in depth how we can store one-to-many relationships. That's what you're asking about, I think. It's like, how do we store one-to-many relationships in SQL? We will get to that, surely. But I just really want to focus on the concept of a bridge, because this is the key thing. Table A.primary key equals table B.foreign key. The foreign keys are only foreign to that table. They are the primary keys to another table. But we say foreign key because it's foreign to the table that is storing it. They are not the keys that uniquely identify the entities in that table. They uniquely identify the entities in another table. Cool. But main idea is that the keys are being stored, and that's how we associate information in one table with information in another table. Cool? Great. So this is how we do this with inner join. That's that syntax. These backticks are not, strictly speaking, a part of the syntax. I put these here to make it clear that these are table names. Okay? I don't believe I have them in the next slide. I do. Never mind. Okay, so this is the where syntax for achieving that same result set. Slightly different. Notice that we still have this select statement that lists the table names that we want in our result set. But now on the from statement, we have both tables. So again, just going back really quickly, whereas before we said from primary table, inner join secondary table, now we have from just both tables. These are the two tables that are involved with this marriage. So we just list them right here on this one from line. And then we don't say inner join on. See, on is like on along this bridge, on this bridge. Now we have where these are equal, where these are the same. But again, same bridge. Table A.foreign key equals table B.primary key.
Why then floats again?
These are table names. That's the only reason why they're not strings. Don't think of them as strings, they're backticks. It's like common markdown syntax for demonstrating or for indicating a primary entity. Okay, but they're not strictly speaking. So when you construct your SQL statements, you will not use these backticks. You will not use them. I just put them here to make it plain that these are table names. Okay.
Does the sequence matter? I mean, like, if I can select those two columns where it's equals from below.
Sorry, say that one more time.
I mean, I put the select first, and then second is where, and then from. I mean,
Oh, you're saying switching these two lines?
yes. So it's
Yes, that might be true. I believe that in SQL 3, the database we're going to be using today would throw an error. but by no means am I, maybe not, by no means would I be surprised if with another database it wouldn't throw that error. But this is just the conventional way of forming the statement, where you have select and then from, and then the filtering. So where is a filtering operator, right? You can see that. It's saying only join these tables where these two are the same. So the result set will contain less data than is contained in the initial table. If we go back to our initial table, notice that, let's see, Emma is not in this final table because her course is null. Okay? Of course, this is like a little bit of a contrived example, but in general, there will be some documents where these two don't match. The result set will almost always be smaller than the tables from which you pulled that data. So that's why we say it's a filtering operator. It returns to us a result only for those documents for which the statement is true. And this is the primary filtering statement, or conditional. Okay.
What does it say there that where is different than interjoin?
Right, so I was just about to get to that, like, maybe unnecessary joke. But the idea, the main takeaway here is that whatever you can do with a where, you can do with an inner join, and vice versa. They yield the same results, but strictly speaking, they are not the same because different things are happening under the hood. And so that's why, I don't know, a couple weeks ago when I was creating these slides, I thought to myself, oh, it's like kind of like string 5 double equals 5. Like it'll return true, but that's just type coercion. If we weren't thinking of like type coercion, or if we were considering type coercion rather, they wouldn't strictly be speaking like the same. They're not strictly congruent, but they do return to us the same result sets. We can use them to get to the same places. Okay? So if you're more comfortable with one than the other, that is fine. It'll be easier to learn another pattern, the inner join pattern, say, if you're more comfortable with the where later on. There's nothing wrong with sticking with one of them. You'll be able to achieve just about every query we ask you to with one of these methods, with a where or an inner join. So if you write all of them with a where, that is fine. Same with inner join if you prefer that pattern. But where and inner join comprise just about like, I don't know, over 80% of all SQL queries. This is like what they're doing, a where or an inner join. So, okay, 2 my Venn diagrams. So let's take 2 simpler tables. These are 2 tables. There's table A, there's table B. Pirates and Ninja are in both tables. Table A has Monkey and Spaghetti. They are not in table B. Table B has Rutabaga and Darth Vader, not in table A. I feel like it's, the coloring is important as well. These are supposed to be bright red to make it very clear. Just not translating as well as I'd like. Okay, the inner join. You guys can see this, right? All of it. Okay, great. So say we want to join table A with table B on the name property, where we want to find out which names they have in common. Again, this would be our syntax. Okay? Notice this star here. That is new. That says include all of the columns in both tables. I could have said select table A.name, comma, table B.name, and had I done that, I would have achieved a result set with just the name columns. I wouldn't be seeing these IDs here. But instead I said all. I said give me the columns in both of those tables. These tables are very simple. They just have ID and name. So it produced a result set with both ID and name for both tables. Okay, that's what star says. Give me all the columns. Select all from table B, select all from table A, inner join table B on table A.name equals table B.name. So find for me the intersection of table A and table B. That is just Pirate and Ninja. They're the only 2 results in my result set. Any questions about this? Yes.
Did that return the ID second table B?
Yes, so I have that here. This is table B, and that's the ID column. I see 2 and 4, so right, same, these names are strings, so it returns to me the strings that are in common, but of course they're not the same objects. And we know that because this is the primary key of pirate in table B. This is the primary key of pirate in table A. Different primary keys, different objects.
I guess my question was, how do we know that it's returning all of the columns from table B also? Or something like, it says we're selecting from table A.
Yes. And you're saying,
Table B.
sorry, what's that?
The question is like, how does it see table B?
Well, I get how it sees table B, but is it returning?
I think you're
How does it know which columns from table B to return?
right. And it's going to return those columns that are the same as those in table A.
Okay.
Yeah. Sorry, I should have made that clear. So say table B had like an H column and table A didn't, we would not see this H column from table B. It's going to return those columns that are in common with table A. If we have ID and name for table A, so it will present to us ID and name of table B. Yes. Thank you for pointing that out. Want to clarify that. That is important.
So in the first example, the courses that return one table, right?
Yes. This is our result set.
Okay, but then for that one, is that one table with or 2 tables?
That's a great question. That is one table. It has 4 columns. And across those columns, we have table A and table B. Of course, this isn't totally accurate presentation of what this will look like in SQLite 3, but I promise it'll be very clear to you which columns are coming from table A and which ones from table B. The basic UI accommodates for that. Yeah.
And they will not be sorted, right? So, like, let's say if Ninja comes before Pirate in table A, the Pirate can come before Ninja in table B.
Yes, that's a great question because that brings up ordering operators, which we will certainly get to in the workshop. There is an order by operator that we can use to order the results in our result set. And we'll get to that, but we're not using an order operator here, so it's unordered result set. Cool. Okay, so this is I'm gonna blow that up. But really quickly, just want to say, so the where equivalent would be select all from table B. Select all from table A, comma, table B, where table A.name is table B.name. Right? I think this is where I have to exit. Yes.
You can also like switch, like select all from table B in join on table A, where switch table A, like placing table A and table B, right?
Yes, you could have done select all from table B, enter join table A. Absolutely. Because think, it's finding the intersection, so it doesn't matter which one is coming first. The intersection is the intersection. It doesn't matter which table you're interjoining onto or into. I like to think of like folding bread. There's like folding something into it and finding the intersection. Not a perfect analogy, but I like to imagine like a folding action where like the matches align perfectly and then we pull the matches out. I can't think of anything I do in real life that really matches the join, but maybe you guys can think of something. Yes, questions? Yes.
So is there a D number, the order in which the elements were added?
Yes and no. Your ID numbers will generally be like 16 bits, so they'll be like 16 characters, and they'll be random, so they won't be like this. You could have like 12,551 is the first ID that is created, and then the next one is going to be 20 million, so that's a contrived example. But I mean to say you can't just look at these IDs and figure out which order they were added, strictly speaking, unless you were to use a separate module to control, it might be my phone, to control the IDs that are generated. So you could use a module that would allow you to say start at here and then increment by 1. But that's not really a good idea for reasons we'll get to when we talk about security.
So if it's not, so there's no like, you said it was random, so there's no like logic other than being random. How do you find elements? Since there's no like a hashing thing happening, right?
So you're saying when
You can easily get elements out of a table. We can have like a lot of like, you know, elements to go through.
There are certain find by IDs properties, or sorry, methods on your table that allow you to do that. But you can also you're always querying for data that you already have, right? So you can't find a record by some piece of data that you don't have. And usually you'll be storing these IDs in a separate data set that we call an index. But I can't really get into that right now. So outside of the scope of this lecture. Any other questions specifically about the inner join or the where? Yes, Elizabeth.
Can you think of primary keys and foreign keys like dominoes?
Like dominoes.
Where they can match up 3 on 1 and the other?
Oh. Yeah.
Just thinking about that.
Yeah, maybe I'm gonna think about that some more. But I like where you might be headed. Maybe I gotta spend more time on it. But yeah, I'm definitely all for finding analogies for these things. So I think, you know, the more we can visualize them, the better. Okay, so really quickly now, let me make this sufficiently bigger. Oh, bigger. Okay. So there is something also called the full outer join. You will not need to use this, but I think it's helpful to just go over them. I also want to introduce you to other kinds of joining to let you know that various patterns are possible. The outer join returns everything from both table A and table B. And it aligns the matching records if there are matches. So again, you have Pirate and Ninja in both, so we'll see them on the same line. And to achieve this sort of delineation, we add null values where there are no matches. So we have monkey here. Since monkey doesn't exist in table B, we have null in table B where monkey would appear if there were a match.
It's like a mapping tool.
So it's like a what?
It's like mapping the data on one table to another.
Yes. Yeah. All right. Well, disappear. Okay. Yeah. It's because I'm not in the slideshow anymore because the font isn't big enough. But basically, this is what that table will look like with the matches only considered. Okay. The left outer join returns everything into table A. Of course, this is a situation in which the order of tables matters. So we would get a different result if we said from table B, left outer join table A. Because then we would get this filled in. With the inner joins, this is the intersection, and that is self-same. It doesn't matter if we say table A, inner join table B, or table B, inner join table A. But with the left outer join, and just about every other join we're about to see, it matters which table appears first. Because the left outer join includes everything in table A, null values where they don't appear with table B. So A is getting, receiving like privilege here, preference, what have you. Right, so that one. Full outer join. This is everything but the intersection. Pretty straightforward. Pirate and Ninja aren't in the result set, so we have null values along each table delineating the differences. Again, this is just for a demonstration of the other ways to join, right? For the purpose of this workshop and for most of what you'll need to know with SQL, focus on the inner join and the where. But I also want to show that other joins are possible, and they make a lot of sense when considered within the context of like these Venn diagrams, I think. A good way to visualize. Yes. We unfortunately we do not have time to go over the outer join, the right outer join, but it also isn't terribly important, to be quite honest. Cool. Any questions about any of what we've gone over? Great. So as I said, this workshop is really just about querying, sending queries into an IMDb database, a subset of it. And so we're going to be using a database called SQLite 3 to do that. And we'll be asking you to download a zip file of that data, and then we'll give you instructions for how to read that file into your database. And then you'll be constructing SQL queries to retrieve data from your database. I believe at the very beginning of the workshop, you're instructed to watch some code school videos to make sure you feel prepared and empowered when you start the workshop. The workshop is really just that. You'll be asked to construct 10 queries, and we'll give you previews of what we expect the results to look like. So you'll know when you get it right. What else? Other tips? That's about it. It's pretty straightforward. You'll also be working by yourselves. I think this is the only workshop for which we actually do this, but for this workshop, because it's just query construction, we've realized that it's not an effective use of pairing. You'll also be, you'll have until 1 tomorrow. Yeah, plenty of time. So this is like this workshop is very leisurely paced. There's very little reason to stress. You have more than enough time to finish it. But we really just want you to think, and as you get to the harder queries, and there are some very hard queries at the end there, we really want you to be thinking about database design and why these schemas are the way they are, right? Because we're going to give you a database. There'll be like 6 or 7 tables. And I'll just go ahead and tell you that some of them don't make a lot of sense. So I want you to be thinking about database design and why whoever, the database admin decides to store, movies like this, or like you'll encounter a join table called roles. You'll have to scratch your head and think about why it was stored in that way. So that's to say, please use the extra time wisely and to really critically, consider and approach the queries and just SQL in general. Cool. Okay, you're off. Please start. Wait, I do have to open the workshop, but yes, please get started.